Bismillahirrahmanirrahim. In this lecture, we will continue our discussion on Zener diode. So, in the previous lecture, we discussed about the characteristics of Zener diode, and we have seen that for Zener diode, we have seen the characteristics was something like this: the voltage current characteristics. So, this is the forward current, and this is the reverse current and the reverse bias voltage. So it was something like this, okay, and the voltage at which the breakdown happens, we will call it as the Zener voltage, and in the forward bias region you will have the characteristics something like this, okay. In the case of this is the case of a practical case, okay, practical Zener diode, okay. So the ideal characteristics also we can draw something like this. The ideal characteristics, the breakdown will happen at Vz and there won't be any change in the voltage. So the breakdown happens at some voltage, and this is known as the breakdown voltage, okay, breakdown voltage, and the minimum current required for this breakdown to happen is known as the knee current, okay, knee current. That means if the current through the Zener diode, or I can say that the current through the Zener diode, we can say Iz, if it is greater than the knee current, you can say that the Zener diode is on, okay. If the Iz, that means the current through the Zener diode, Iz means the current through Zener diode, okay. If Iz is less than Izk, we can say that the Zener diode is off, okay. So, and also we have the maximum limit for the current also, and this is the maximum limit, and which is known as the Izm, okay. This is the maximum limit for the Zener current. So if the current through the Zener diode, if it become greater than Izm, what will happen? The Zener diode will damage, okay. So we want to avoid this condition. So we can say that, we can conclude that the current through the Zener diode should, current through the Zener diode should satisfy the condition, okay. What is this condition? Some conditions, okay, we can say some conditions. What are those conditions? The current through the Zener diode should be greater than Izk, greater than or equal to Izk. That means then only it will become on, okay. So we want to make it, turn it on, and the current should be less than or equal to Izm. If it become greater than Izm, then it will damage, okay. So this is regarding the protection, okay, protection of Zener diode, okay. If the current Iz become greater than Izm, the possibility of damage is very high. That means the Zener diode will damage. So we want this condition, as we mentioned, the current through the Zener diode should be greater than Izk, and the current should be less than Izm. So I can conclude this condition like this: the current through the Zener diode should be less than Izm, and also it should be like, if you read like this, in this way, the current should be greater than Izk, or I can say that Izk should be less than Iz and should be less than Izm. So this is the operating region for Zener diode, okay. So with this notion in mind, we will discuss about the voltage regulator, one of the important application, of Zener diode is nothing but the voltage regulation, or we will design a voltage regulator. So how to design a voltage regulator? So we will discuss about the design of voltage regulator. Okay, voltage regulator. So what is voltage regulator? Voltage regulator is a circuit which is used to regulate the voltage. Suppose you have a, you can say this is voltage regulator. I will use the abbreviation VR. Okay, this is voltage regulator. So you have an input. This input may be the output from a rectifier after filtering. You know that this is something like this. Okay, after filtering operation, that means you have an AC signal, and you may use a full wave rectifier. After that you have a capacitive filter or something like that, anyway filter. Okay, so you will get the output here like this, something like this, and after filtering operation you have the signal like this, right? This is the voltage output, okay, V out, and this signal you will give as the input to the voltage regulator. Now the voltage regulator actually sees the signal which is changing. Okay, it is having a maximum limit and it is having a minimum limit. Okay, so you can see that the signal is changing between maximum and minimum, but the voltage regulator will give you a constant DC. Now you can see that this is a perfect DC. So you can use the voltage regulator to regulate the voltage, or to maintain the voltage at a constant level. So this is one of the main application of the voltage regulator. For example, you can consider a voltage regulator like this. The input is changing. Okay, this is the input. Maybe this is changing from maximum 8 volt and minimum this is 6 volt. Okay, so this maximum 8 volt and minimum 6 volt, but the output, if you want to fix at 5 volt, you will get a constant 5 volt output. Okay, this is the V out and this is the V in. Usually you will be fixing this output which is less than this minimum. That means your V out will be always less than your V minimum. You should satisfy this condition, otherwise there will be fluctuation. So you can maintain a voltage which is less than this V minimum, and you can make it constant or as a perfect DC. So this is one of the important application of the voltage regulator. Now we are going to design a voltage regulator. So you know that we have for a Zener diode, you know that whenever Zener diode become on, when it become on in reverse bias, not in forward bias. Okay, in reverse bias, when it become on, the breakdown will happen, right? The breakdown will happen and the voltage will be Vz, or I can say like this. This is the Zener diode. So the voltage across the Zener diode, because you can see here this is N and this is P type semiconductor. So here you will give positive and here you will give negative. So this is the power supply. Okay, power supply you are giving. You are giving the supply like this. That means this is reverse biased. So in reverse bias, there will be a current from this positive to negative. So you can say that there will be a current something like this, which is going from positive to negative. So you will get a positive sign here and negative sign here, and the voltage which is appearing across the Zener diode will be Vz. You know that in an ordinary diode, when it become, we can say that in a standard diode, when it become forward bias, the voltage across the diode will be 0.7, but in a Zener diode, the voltage across the Zener diode will be Vz, and it is working in reverse bias. Okay, this is the difference. So this is the case of the standard standard diode, and this is the case of the Zener diode. Okay, and the Zener diode will be working in forward bias. And you know that in any diode circuit you will always use a resistor. You will always use a resistor. Why you are using a resistor? If you are connecting a power supply, you will always use a resistor, right? Here in Zener diode also you will use a resistor. In Zener diode circuit also you will use a resistor. Okay, so this is the case of the standard diode, and in Zener diode circuit also you will use a resistor. Why you are using a resistor? To limit the current. And in the previous slide I have already explained that Zener diode should, this is the operating region for Zener diode, right? Operating region for Zener diode. So we have to maintain the current through the Zener diode within this region. Otherwise what will happen? Otherwise we cannot, if we cannot maintain the current, then it will not work properly. For example, if the value of the current Iz become less than Izk, or the knee current, what will happen? This is the knee current. Okay, so if it become less than the knee current, then it will become off, right? So the current should be greater than the knee current. Now if the current through the Zener diode, if it is exceeding the maximum limit, what will happen? The Zener diode will damage. So we have to maintain the current through the Zener diode in a proper way. So how to maintain the current in a Zener diode? Current through the Zener diode? By connecting a resistor. Okay, so resistor is very, very important. So we will discuss with a problem of designing a voltage regulator. Okay, so before that I will just show you the circuit diagram for voltage regulator. Okay, for circuit diagram for voltage regulator. Now you can see you will be always using a Zener diode for in a voltage regulator. Now you will be taking the output here. This is your V out. Okay, because you want the voltage V out. So you know that whenever the Zener diode become on, you will get a voltage plus minus Vz, and we have to give here supply. Now you see here you will be giving a supply, maybe changing like something like this, as I mentioned before. So it may be changing. Okay, now you will connect like this, but if you connect like this, you can see that the current, actually the current through the Zener diode may go to infinity, because there is no resistor in the circuit. We are assuming this Zener diode as a perfect Zener diode, an ideal one, which is having no resistance, internal resistance. So what will happen? The current become infinity. The current become infinity. So what will happen? Your current through the Zener diode become greater than your maximum limit in the Zener diode. Okay, then what will happen? It will damage. So to limit the current, what we will do? We will add a resistance in series here. So we will add a resistance, and this resistance is known as R. So this is to limit the current. To limit the current, we will add the resistance. Now you can get the voltage across this V out is nothing but Vz. Now you will be driving some load. Maybe sometimes you will be using it as a mobile phone charger or something like that. So what we will do? We will connect a load. We will show the load also. But you cannot expect that your load is fixed. For example, if you are using it as a mobile phone charger, sometimes you will be using different mobile phones. So different mobile phones will be having different resistance, load resist. We can say different mobile phones will be having different internal resistance. Okay, at the charging point. So that means your load is not fixed. Your load may be changing. So you can say that your load is changing load changes. Okay, that means your load is changing. We can say that load change in the limit, we can assume something RL minimum to RL maximum. Okay, so we have to be very careful about this. Now you see here, now the voltage regulator circuit diagram is something like this. You have a resistance R, you have a changing input voltage which is changing between the limit V in minimum and V in maximum, as I mentioned before. Now you have something like a Zener diode like this. The voltage across the Zener diode will be always constant, it is Vz. Now you have a load, and across the load you are measuring the output, and the load is not fixed, your load is changing between the limit RL minimum and RL maximum. Okay, I hope that this is clear. Now you have to be very careful for the Zener diode. The current through the Zener diode, I will say this is the current through the Zener diode, IZ. This IZ should satisfy some condition. That means it should be in the operating region. And what is the operating region? We have already explained it. Operating region, this one is the operating region. That means I will explain it once again. Operating region means the current should satisfy a condition that it should be greater than the minimum value. What is the minimum value for turning it on? It is IZK. So the current should be greater than IZK, and also the current should be less than IZ maximum. If the current become less than IZK, what will happen? That the Zener diode will turn off and it will not work at all, and it will not work as a good voltage regulator. Now if IZ become less than IZM, then it will work fine. But if it goes above, so these are all the operating conditions. Okay, these are all the operating conditions. But if IZ greater than, if IZ less than IZK, your Zener diode will turn off, and if IZ greater than IZM, your Zener diode will damage. Okay, so you don't want this condition. This is not a good condition, and this is the operating region, okay, between this limit. So the current should satisfy the condition IZ should be less than the maximum limit. This is the maximum limit, and it should be greater than, we can, if you read in this way, it should be greater than IZK. Okay, that means this is the minimum limit. That means the current in the Zener diode should be between some minimum point and a maximum point. Okay, it should not, that means it should be in a suitable operating region. So with this notion in mind, we will discuss a problem, design problem. So design problem. So design a voltage regulator using Zener diode with the following parameters. Okay, parameters or specification. Okay, it is given that your Vz is 15 volt. Your minimum current required for the Zener diode to turn it on, that is known as IZK, is 0.25 milliampere. Then PD max is given. PD max is equal to 1 watts. That means the maximum power that it can accommodate is 1 watts. Then RL minimum load that you can expect at the output side is 1000 ohms. RL maximum that you can expect at the output side is 3000 ohms. Okay, these are all the parameters. So first of all, we will draw the circuit diagram. Solution, we will draw the circuit diagram something like this. This is the Zener diode. Now your input is also given. V in minimum is equal to 24 volt and V in maximum is equal to 28 volt. Now your input is changing from V in minimum, which is equal to 24 volt, and V in maximum is equal to 28 volt. Okay, now you can see here this is your Zener diode. So you can connect like this, and there is a load. The load is also not constant. Your load is also changing between RL minimum, which is equal to 1000 ohms, and RL maximum, which is equal to 3000 ohms. Okay, now I told you we want the current through the Zener diode in a proper way. It should have a current which is IZ, and this IZ should satisfy some condition. Your IZ should be greater than or equal to IZK, and IZ should be less than or equal to the maximum current. So this is the minimum limit and this is the maximum limit. Okay, so for limiting the current we should put a resistor, this R. Now we are going to design, that means we are going to find how much this R is. Okay, so we want to find, so in this design problem the main objective is to find out what is the value of R. Now IZM is not directly given. You can see here IZM is not directly given, but something is given which is known as PD max. So we have PD max which is equal to 1 watts. We have VZ. What is VZ? VZ is also given, VZ equal to 15 volt. So your output should be 15 volt, because you can see this Zener diode is in parallel with the load resistance. So it is 15 volt, because when the Zener diode become turned on, the voltage will be 15 volt. So you know that the current, so this is the maximum power dissipation, maximum power dissipation, and the voltage. Now you know the power and you know the voltage. Now you can find the current maximum by using this. IZ maximum is equal to PD max divided by VZ. This is nothing but 1 watts divided by 15 volt. So you will get this as 66 milliampere. So with this notion in mind, we will discuss in detail about the design of the resistance R. Okay, so we have the resistance. I will redraw the circuit. We have the resistance R and Zener diode, and we have RL minimum and RL maximum, and the voltage is changing between the limit V in minimum and V in maximum. Okay, so I will first write the minimum condition. I will I will classify our condition into two, because we have the condition that our current should be, IZ should be greater than IZK, and IZ should be less than or equal to IZM. So this is the operating region. So we will write, so this is the minimum condition, and this is the maximum limit. So according to this minimum and maximum limit, I will write the two condition. So this is the minimum limit and condition according to the maximum. What is the minimum condition that we have seen? That means IZ should be greater than or equal to IZK. Now we are talking about the minimum condition. That means we are talking about a condition that we want to just make it, at least we should ensure that our Zener diode has not gone into the off state. Okay, so how to ensure this? The current, we will talk about the minimum current through Zener diode. The minimum current through Zener diode will happen only if the supply coming from here because the current is coming from the source, that should be minimum. And the current through the Zener diode will be minimum if the current through the load, that means this current, is maximum. Is it clear? Suppose you have a current of some 100 milliampere, okay, and 99 is flowing here, then this current will be only 1 milliampere. So what does it indicate? It indicates that the current through the Zener diode will be minimum only if the maximum current flows through the load and the current which is coming from the supply is minimum. So in minimum condition, the current from supply voltage should be minimum, then current through load RL should be maximum. Then, so if these conditions are met, then the Zener diode current will be minimum. Okay, so you should understand this idea. Okay, this is very, very important. Now you know that the voltage across the Zener diode, we know voltage across the Zener diode is Vz. So the voltage at this node is also Vz. Now how to find the current? Because we are talking about the minimum condition, so we will talk about the minimum voltage. So the minimum current which is coming is in this direction, okay, is nothing but V in minimum minus Vz divided by our resistance R. Actually we don't know R, but we will write the equation and after that we will solve it. Okay, V in minimum minus Vz by R. So this is the total current which is coming. Out of that, maximum is flowing through the load. So the current through the load will be maximum when the resistance is minimum, because you know that the current equal to V over R. If the resistance is minimum, the current will be maximum. Okay, so we will find that this current, what is this current? The current will be maximum when the resistance is minimum, but you know the voltage is Vz, so at this point also the voltage will be Vz. So Vz by RL minimum, that is the current through the load. Now this is the total current which is coming from here, and some current is leaving to the load, you can see. So the remaining current, so you just need to subtract this, then that will be the current. Now this is the current Iz, which is minimum Iz through the Zener diode. Okay, now I will write it here itself. Okay, now you got the equation, and this current, whatever you are getting here, whatever current you are getting here, you can see this current, whatever you are getting here, this whole quantity should be greater than or equal to Izk. So this is what the minimum condition. So now we will solve this in our case. Okay, I will use the next slide. So I will rewrite this equation again in the next slide. So V in minimum minus Vz over R minus Vz over RL minimum. This quantity, the whole quantity, should be greater than or equal to Izk. So V in minimum is given in the problem. You can say that V in minimum is given, it is nothing but 24. Okay, so 24 minus 15 over R minus 15 over 1000 should be greater than 0.25 milliampere. Okay, so you will get here, this is 9 over R minus 15 milliampere should be greater than, this is ohm, this is volt, so this become 15 milliampere, so 0.25 milliampere. That means 9 over R should be greater than or equal to, you can say greater than or equal to 15.25 milliampere, or I can say that R should be, or I can say like this, 9 over 15.25 milliampere. Okay, this is 9 volt, that should be, okay, greater than R, which implies R should be less than 9 volt by 15.25 milliampere. That means R should be less than 590 ohms. So you have to put a R which is less than 590. For example, if you are putting a R of 600 ohms, what will happen to the current? The current become very less and the Zener diode will go to off state. So you should ensure the condition that your R should be less than or equal to 590 ohms. Now, so we have got some idea regarding R. Now, this is not enough. We want to find the exact R. So this is according to the minimum condition. So this is what the equation that we have got using the minimum condition. Now we will use the design. What should be the condition related to the maximum case? So in the maximum case, what is the maximum situation? That is, you see here the current through the Zener diode should be less than IZM, and you know that this IZM we have already got it as some 66 milliampere, right? We got it as 66 milliampere. Now I will draw the circuit diagram again to explain this idea. So you have RL minimum and RL maximum. This is the limits in which it is changing. Okay, now we have something like input is changing, V in minimum and V in maximum. Now listen carefully, this is R. Okay, now you can see here we are talking about the maximum current condition. So the voltage across the Zener diode, okay, I will use another color which is suitable one. Okay, the voltage across the Zener diode is will be something like this. Okay, this is Vz. Okay, now the voltage at this point is Vz, and this also Vz, everywhere it is Vz. Okay, now let us assume the current which is coming from this. Suppose this current is maximum. We are talking about the maximum current. Now we have the current through the Zener diode as Iz, and we want to limit this maximum current, and this is also maximum. If maximum current is coming from the source and maximum is going through the Zener diode, that means that the current which is going into the load should be minimum, right? So the total current from source is maximum. When it will happen? When this will happen? You can see here the current which is coming from the source will be maximum when the input is maximum. So that means V in maximum. Okay, and Vz is constant, and the current, if okay, the current through the load RL is minimum. When it will become minimum? It will become minimum when the load is maximum. That means the load is maximum, because current equal to, current equal to voltage by resistance. When the load become maximum, the current become minimum. So if these two conditions are met, then what will happen? The current through the Zener diode will be maximum. So we will write the equation. So you know that this is Vz and this is V in maximum. So the maximum current which is coming, total current is coming, is given by V n max minus Vz divided by our R. Okay, our R. Now this is the total current which is coming, total current. Now the current through the load which is minimum, how to get it? You know the voltage is Vz by RL maximum. Okay. Now this is the total current, this is the current through load. Okay, through load. Now if you subtract the current through load from the total current, you will get the current through the Zener diode, and this quantity should be less than, as I told you before, this quantity should be less than or equal to the maximum current. Otherwise what will happen? The current will exceed the limit and the Zener diode will damage. So I will write this equation once again. You can see that V in maximum minus Vz over R, this is the total current, minus the current through the load is the maximum when the current through the load is minimum when the load is maximum. Okay, so this is maximum. This current total should be less than or equal to, as I have told in the previous slide, should be less than or equal to IZM. Okay, now I will substitute. We know that V in maximum, in the problem it was given V in maximum, you can see here it is 28 volt. It is 28 volt. 28 volt minus Vz is 15 volt divided by R minus Vz is 15 volt divided by RL maximum is 3000 ohms, and this number should be less than or equal to 66 milliampere. Now this become 13 over R minus, this is become 5 milliampere, should be less than or equal to 66 milliampere. That means 13 over R should be less than or equal to 71 milliampere. That means R should, that means I can say this implies 13 over 71 milliampere should be less than or equal to R, or I can say R should be greater than or equal to 13 over 71 milliampere. You will get it as 183 ohms. So I can conclude now, by using the minimum condition, you have got the idea, you have got the value of R, as R should be less than 590. R should be less than or equal to 590 ohms. And by using the maximum condition, you have got R should be greater than or equal to 183 ohms. So what does it signify? What does it show? So I will write it in the next slide. So the minimum condition will give you R should be less than or equal to 590 ohms, and the maximum condition has given you R should be greater than or equal to 183 ohms. So if we draw the characteristics of the Zener diode, this is the reverse voltage and the reverse current. So I can draw the characteristics of the Zener diode, this ideal one, with Vz, and this is the minimum current Izk, and this is the maximum Izm, and according to this, this is the minimum and this is the maximum. According to this, we got the condition that R should be less than or equal to 590, and according to this, we got the condition that R should be greater than 183 ohms. Now, if you put a low resistance, for example, if you are putting 100 ohms, if you reduce the resistance, the current will increase. Then what will happen? The current through the Zener diode also will increase and it will damage the Zener diode. So, our condition is that R should be less than or equal to 590 ohms and R should be greater than, I can say, 183 ohms. So I have now got 2 points, minimum and maximum. So which is the optimum? Because these are all the operating region. Out of this operating region, I can select any point. I can select any value of R between these two, minimum and maximum limit. Okay. Now I can say that the best way to choose is by taking the average. So if you take the average of this point and this point, you can get somewhere here, right? So this is the good point to choose. So this is the Q point that you can choose, or the operating point you can choose. Okay, operating point that you can choose. So the better way to choose the R is nothing but just take the average, 183 plus 590 divided by 2. Okay, so you will get the answer as 386.5 ohms. So you can also take the average in another way. Okay, like R is equal to square root of 183 into 590. This is also possible, but anyway, you can follow the simple average. I don't want to make more complicated. So the answer is something, the average of the minimum and maximum values. I hope that this is clear to you. Thank you.